Okay, next up is a classic ladder problem. It's not going to be the simplest of examples. Pardon me. Alright, a 15-meter long uniform ladder weighing 500 newtons rests against a frictionless wall. The walls are usually treated as frictionless in this case, having to deal with the normal force and how it changes and how the friction force against the wall changes. As a consequence, it gets kind of tricky. So usually the problems will leave it out. Alright, the ladder makes a 60-degree angle with the horizontal. First part, and we'll stop after reading this because the second part's a total change in this case. Find the horizontal and vertical forces the ground exerts on the base of the ladder when an 800 Newton firefighter has climbed 4 meters along the ladder from the bottom. Okay, this will take me a moment to draw out. I will actually switch how I've done the drawing when we do part B because it's too easy to get trapped into drawing things the same way every time. What happens if you happen to see a problem given to you where things are not that way? Alright, so we've got the ladder in yellow, we've got that there. Oops, I don't want red yet. Length of the ladder is 15.0 meters and it is uniform. The weight is given. So the weight of the ladder is 500 newtons. Alright, the weight of the firefighter is 800 newtons. Angle of the ladder is 60 degrees from the x-axis, from the horizontal. And I'm going to call it D. The distance the firefighter is along the ladder is 4.0. Suppose that's not 4.00 meters. Okay. So here's the drawing so far. We will put the firefighter in here. The distance to them will be the distance D. Angle theta will be down here. What forces act? Well, it's uniform. That means we find the midway point, and the weight of the ladder will act from there. The firefighter is standing on the ladder. They'll be supported by a normal force due to the ladder, but that means the normal force due to the ladder and the weight of the firefighter must be the same thing. So we'll have the weight of the firefighter. Actually, it's longer. I should draw it properly. Will be right here. All right. It's asking us to find the forces due to the wall and the ground. Well, the ladder experiences a normal force due to the wall, which means it must be experiencing a static friction force due to the ground, because that's the only way we get another horizontal force that can cancel. And then there must be a normal force due to the ground. So these are all of the forces. All right, let's start with the sum of forces in X. This is going to have to be Fs minus normal due to wall is equal to 0. Sum of forces in Y, the normal due to the ground and the weights must be offsetting each other. Okay, so this tells us the size of the friction force and the normal due to the wall must be equal. This tells us the normal due to the ground. We actually know it. It's the weight of the firefighter plus the weight of the ladder, so it's going to be 500 newtons plus the 800 newtons. So 1300 newtons. We've got one of the three things we're looking for. The other two are going to require torque. For that, we need to pick a center of rotation. You can pick it anywhere. I tend to pick the contact point with the ground because notice it makes the torque due to the normal 0, and it makes the torque due to the friction 0. Very convenient things to get rid of. Alright, I started recording this video at a bad point, so we're going to do part A in one video and part B in another one. So we'll finish this one up, and then we'll do a separate video for part B. Alright, so torque. Well, this is inconvenient, because we'd be taking our R coming across here and then have to curve over and figure out our phi. That's inconvenient. But remember, there are several different ways of finding torque. It's r times F times sine of phi, or it is r perpendicular times F, or it is r times F perpendicular. We're actually going to do it this way, r perpendicular. So r perpendicular to get to the first force, the second force, so to the firefighter, to the weight of the ladder, and then all the way up to here to get the r perpendicular for the wall. These are all really easy to find. The distance along this triangle is L over 2, and then we went the cosine component of it. Along here it's D, and then we went the cosine component. Along the other side, you notice it's the full length of the ladder, and then it is L sine theta. So we can figure all of them out pretty easily. Now let's think about positives or negatives. The way it's drawn, the torques due to the weights will be negative. So we have minus d cosine theta times weight of the firefighter minus L over 2 cosine theta times the weight of the ladder. Then we have plus L sine theta times the normal force due to the wall, and that must equal 0. All right, rearranging this. L sine theta times normal due to the wall is equal to d cosine theta, weight of the firefighter, plus L over 2 cosine theta, weight of the ladder. Move the L sine theta over, and we have our answer. D cosine theta, weight of firefighter, plus L over 2 cosine theta, weight of ladder, all divided by L sine theta. All right, so 4 times cosine of 60 times 800 newtons, plus half of 15 is 7.5 times cosine 60, times the weight of the ladder is 500. I'm getting the answer for that. Then I'll divide by the length, 15 meters, times sine of 60. And we get 267.5 newtons. And that also tells us the friction force must also be in size 267.5 newtons. Or 268 if you want to round it up. Okay, that's part A. We'll come back and do the second part in another video.